To start with, let's get a better understanding of how far our closest neighbor is, and to gauge this we can use the fastest space apparatus invented by humans, Helios 2, a satellite system dedicated to sun observation. Its speed is 157,000 miles per hour, which is about 0.023% of the speed of light, rather impressive. The resources for colonization of the New World are packed, just waiting for the signal to launch. We're heading to the Alpha Centauri system. 3, 2, 1. Don't worry, there's nothing wrong with your internet connection, the picture really stays the same. Right now, we're moving faster than anything ever created by humans, but on the cosmic scale, we're practically standing still. We'll be able to reach the nearest star system only in about 18,000 years. That's the reality of things. Only when you realize the scale of these distances can you understand how important it is to study our cosmic surroundings if we ever stand a chance to wake up and enjoy the sunshine from a different sun. The costs are too great to do this at random, which is why Alpha Centauri became one of the first star systems to be studied so closely. People notice the main star, or, more precisely, a pair of stars, Alpha Centauri A and Alpha Centauri B. Both are sun-like yellow dwarf stars that appear as a single star to the naked eye. The third brightest star in the night sky has captivated the attention of scientists since prehistoric times, including the Sumer civilization and the ancient Egyptians, and is even mentioned by Ptolemy. But the systematic, scientific study of the star system only started in 1915, when British astronomer Robert Innes discovered the third star in Alpha Centauri, a red dwarf that was named Proxima Centauri. To this day, it remains the closest known star to the Sun. The open and detailed study of our nearest star occurred at the same time as the beginning of the golden age of science fiction and space opera, which led to a huge rise in popularity for Alpha Centauri. It has appeared and continues to appear in the works of sci-fi writers, artists, movie directors, and even composers. The proximity of another star has stirred the imaginations of creative people, from the Strugatsky brothers to James Cameron, because there, in a different world under a different sun, could reside and develop entirely new civilizations. And so Alpha Centauri forever earned its place in people's minds as the location with the greatest potential for extraterrestrial life. However, the reality is much grimmer, as it often happens. The active study of exoplanets planted a new seed of hope for discovering signals or at least circumstantial evidence of life on faraway planets. Scientists found 2 planets in the habitable zone of the Alpha Centauri system, Centauri AB and Centauri BB. Unfortunately, after more detailed study, both planets turned out to be uninhabitable, at least as we know it, and so astronomically speaking, these planets were temporarily shut down. But everything radically changed in 2016. After years of intensive searching, scientists managed to find, and more importantly, confirm the existence of an exoplanet in the Alpha Centauri system. What's more, this exoplanet orbits our closest neighbor, Proxima Centauri, and was subsequently named Proxima Centauri B. The planet is approximately 4.22 light-years away, and it's incredible that it was discovered in the first place, given its mass is only 1.1 times that of Earth's. Confirming its existence required a lengthy, labor-intensive process that involved measuring the planet's radial velocity as it crossed the disk of its parent star, Proxima. But the surprises didn't end there. Proxima Centauri B had even more to reveal. In April and May of 2019, the Parkes Observatory in Australia recorded strange radio signals over the course of 30 hours, potentially coming from Proxima Centauri B at a frequency of 982.002 MHz. How did scientists arrive at this conclusion? Answering this fully would take some time, but here's the essence of it: the shift in the frequency of the signal aligned with the orbital movement of Proxima Centauri B. Then, after this initial discovery, the signal mysteriously disappeared. In 2020, scientists made a second attempt to re-establish a connection, but it was unsuccessful. By 2021, researchers calculated the probability of a species existing in our nearest star system with the capability to produce radio communication is 10 to the power of -8, meaning the chance of the signal being artificially created was extremely low. Further studies have continued on Proxima Centauri since 2017, as astronomers closely monitored its activity using the Atacama Large Millimeter Array, ALMA. Proxima, classified as a red dwarf, exhibits extraordinary activity, including coronal ejections known as flares. In one instance, the brightness of a flare increased 1,000-fold within 10 seconds, lasting about 2 minutes in total. Sadly, this level of stellar activity suggests that Proxima Centauri b would be exposed to such intense radiation that it would likely render the planet inhospitable. Since these flares occur frequently, any atmosphere that might have once existed would have likely been destroyed and dispersed into space. Another significant barrier to habitability for Proxima Centauri b is its short orbit around Proxima, completing a full cycle in only 5.12 Earth days. This close proximity to its sun means it would be subjected to extreme heat, even from a red dwarf star, enough to make liquid water on its surface unlikely. Consequently, the conditions on Proxima Centauri b likely make it inhospitable to life as we know it. Yet the mysteries around Proxima don't end there. Using the espresso spectrograph mounted on the European Southern Observatory's Very Large Telescope, VLT, between 2020 and 2022, scientists observed the transit of another mysterious, smaller object, eventually leading to the discovery of a new planet, Proxima d. This planet, identified through radial velocity measurements, is among the most promising many Earth's for future study. Proxima d's radius is estimated to be about 0.8 times that of Earth's, while its mass is about twice that of Mars. Scientists are still evaluating whether Proxima d could be viable for habitability, but if Proxima d is indeed uninhabitable, then what value does this discovery bring? The potential uninhabitability of planets like Proxima Centauri b and Proxima d actually contributes profoundly to our understanding of exoplanetary systems and the unique conditions necessary for life to thrive. These findings underscore just how rare and delicate the balance for habitability may be. Studying planets orbiting nearby stars like Proxima Centauri helps refine our criteria for what makes a planet potentially habitable. It also sharpens our tools for detecting atmospheric conditions, assessing solar radiation tolerance, and understanding orbital effects on exoplanets. Moreover, these discoveries inspire technological advancements in observational astronomy. They remind us of the critical need for high-precision instruments, such as spectrographs that can capture the faint signatures of distant, small planets. Every study expands our knowledge, bringing us one step closer to finding a truly habitable planet beyond Earth. The endeavor may yield no immediate prospects for colonization, but the knowledge gained is invaluable, guiding future explorations and informing us about the cosmic environments we might one day explore. So, while Proxima Centauri b may not support life as we know it, each discovery around Proxima offers vital insights into the complex interplay of factors that make planets livable. You have to view this discovery through a broader lens, one that considers the future. The presence of interesting, varied worlds in our nearest star system, even if not yet suited for human life, opens up new horizons for research and exploration. The existence of Proxima Centauri b suggests there could be countless other exoplanets waiting to be found, beyond our current reach. What do we mean by current reach? Right now, astronomers mainly rely on two methods for detecting exoplanets. The first and most widely used technique is the transit method. In this approach, telescopes monitor stars over extended periods, watching for slight but consistent dips in brightness. Such changes indicate that a planet is passing in front of its host star, briefly blocking some of its light from our view. The second, more complex method is known as Doppler spectroscopy, or the radial velocity method, often called the wobble method. When a planet orbits a star, gravity binds them together. Rather than the planet orbiting in a perfect circle around the star, both objects orbit around a shared center of mass, known as the barycenter. For instance, the barycenter of our solar system lies just outside the Sun's surface, causing the Sun itself to wobble. This wobble affects the light waves reaching Earth through an effect known as the Doppler shift. As the star moves away, light waves stretch, redshift, and as it moves closer, they compress, blue shift. Astronomers search for such periodic Doppler shifts to infer the presence of an orbiting planet. While effective, these methods work best for detecting large exoplanets, as larger bodies block more light or create more pronounced wobbles. Discovering smaller planets, like Proxima Centauri b, presents a much greater challenge. The data is telling, only 36 out of the 32,073 planets in NASA's Exoplanet Archive have a mass smaller than Earth's. We mainly detect large giants, which tend to be less habitable than smaller, Earth-like planets. So, what's the next step for exoplanet discovery? Scientists have a clear answer: the James Webb Space Telescope. This state-of-the-art telescope, launched amid excitement from astronomers and enthusiasts alike, has the power to transform our understanding of astronomy. In addition to its main goal of studying light from the universe's earliest galaxies, the telescope has a crucial mission: the search for habitable exoplanets. With its advanced imaging and spectroscopic capabilities, the James Webb Space Telescope could change the way we perceive not only the cosmos but our place within it. The James Webb Space Telescope, JWST, is equipped to capture images of Proxima Centauri B in such detail that it could reveal whether the planet has an atmosphere. If an atmosphere exists, the winds would redistribute heat across the planet, affecting how much heat radiates in infrared as it orbits. Since Proxima Centauri B's rotation means we mostly see its cooler side, the heat distribution could indicate the presence of an atmosphere. A consistent heat level would suggest atmospheric winds, while significant fluctuations would imply the planet lacks an atmosphere. For the first time in astronomical history, we have a chance to directly observe exoplanets in ways that go beyond mere detection. This capability opens a whole new world of opportunities, not only to confirm the presence of an atmosphere but to analyze its components. For instance, JWST can detect the presence of ozone, which would leave distinct spectral lines in the infrared spectrum. Hypothetically, if an alien civilization observed Earth, the presence of ozone lines would signal our planet's oxygen-rich atmosphere, suggesting life. JWST could allow us to make similar determinations about other planets. In addition, the telescope can measure critical parameters like a planet's axial tilt and its size relative to its host star. All of these factors will become crucial in exoplanet studies as JWST begins its full mission at the Lagrange point L2 in mid-2022. Until then, it is undergoing calibration to prepare for its initial observations and to unveil the universe's secrets. JWST represents the immediate future of exoplanetary studies, opening doors to the discovery of habitable worlds. But looking even further into the future, we find the prospect of traveling to these newly discovered worlds. While interstellar travel might sound like science fiction, initiatives like Breakthrough Starshot aim to make it a reality. This ambitious project seeks to create spacecraft with light sails capable of reaching the Alpha Centauri system within 20 to 30 years, at 15 to 20% the speed of light, propelled by superpowerful lasers. This speed could make it feasible for humanity to reach another star system in just a few decades. Breakthrough Starshot has already caught the attention of prominent space enthusiasts, including Facebook's founder, Mark Zuckerberg. The project involves launching a base ship into orbit that would carry a fleet of smaller spacecraft, each outfitted with a light sail. The challenging part is establishing an array of powerful lasers positioned worldwide, working in sync to provide continuous acceleration by taking advantage of Earth's rotation. Each small spacecraft, measuring around 4 by 4 meters, would be powered by lasers as strong as 1 terawatt-hour. For perspective, this energy is comparable to the 121 terawatt-hours used annually for global cryptocurrency mining. With backing from notable figures like Yuri Milner and the late Stephen Hawking, Breakthrough Starshot envisions sending thousands of these spacecraft toward Alpha Centauri. The estimated project cost, around $5 to $10 billion, seems modest considering that JWST alone cost $10 billion. However, both projects promise transformative scientific value. In summary, with JWST, we are at the brink of a revolution in exoplanet study, enabling us to observe distant planets in incredible detail and possibly detect signs of habitability. Looking further, Breakthrough Starshot could push the limits of human exploration by aiming for interstellar travel. This approach holds the promise of advancing humanity's understanding of the cosmos, inching closer to the stars while building on the awe and curiosity that drives our exploration of space. Imagine if we could send probes to the stars. It would be the penultimate step toward preparing for the colonization of distant worlds. This exploration would provide vital information about potential destinations and could answer the essential question: how many worlds are there, and what are the chances of finding life as we know it, or even more exotic forms, like those imagined by science fiction authors? There's also the tantalizing potential of discovering non-standard life forms. For instance, Proxima Centauri, with its frequent, intense flares, bombards its exoplanet Proxima B with harsh radiation. These conditions would likely be fatal for most Earth-like life, but hope remains for alien existence. In theory, life on Proxima B could still survive beneath its surface or in deep water, shielded from ultraviolet rays. Some organisms might even convert UV radiation to biofluorescent light, thanks to protective proteins, possibly creating glowing, biofluorescent life beneath Proxima B's crust. Earth provides a real-life example of biofluorescent adaptation in coral polyps, which contain proteins that absorb UV radiation and emit longer wavelengths of light. If life on Proxima B adapted in a similar way, the planet could exhibit a detectable glow at certain wavelengths, perhaps even within the visible spectrum. This glow, if present, could be observable by the advanced technology of the James Webb Space Telescope. The study of exoplanets is crucial not only in answering the age-old question, are we alone, but also in expanding our developmental horizons, ultimately facilitating the spread of humanity across the stars. Time will tell if Proxima Centauri B is one of a trillion similar worlds or a rare exception. For now, it's up to us to pursue these questions, guided by human perseverance and curiosity, our greatest allies in the quest to conquer space.